Hello everyone, my name is Deepraj Soni. It is my pleasure to present Design Space Exploration of Modular Multipliers for ASIC FHE accelerators. I would like to acknowledge my co-authors from NYU Abu Dhabi and NYU New York. Currently, I am pursuing PhD at NYU Tandon School of Engineering. My research work primarily focuses on hardware implementation of fully homomorphic encryption primitives and architecture. Any user can outsource its computing to server in today's world. For that, data has to be encrypted so that it remains secure when the data is in transit or in storage. But once the data is received to the server for computation, it has to be decrypted. This means that during the computation process, the decrypted data is susceptible to interception and exploitation by attackers. To minimize the risk of data being compromised during computation, it is important to implement appropriate security measures such as access controls, firewalls, multi-party computation, or intrusion detection systems. However, fully homomorphic encryption or FHE provides highest security guarantee for outsourced computing. FHE enables computing over encrypted data. Hence, the server does not need to decrypt the data for computation. As the server never decrypts the data, the attacker cannot access private user information. Now let's look at FHE ciphertext. FHE schemes are based on learning with error. Here, ciphertext has two polynomial modulo xn plus 1, where n is polynomial degree and it can be as large as 128k and modulus q can be as large as 1600 bits. Ciphertext size could be 25 megabytes or even higher. On this large ciphertext, modular arithmetic is performed, which makes modular multiplication computationally most complex and crucial part of FHE. General purpose computer generally does not have the dedicated modular multipliers for this kind of computation. Hence, software implementation of FHE is million times lower than unencrypted computation. To address this issue, a dedicated FHE accelerator with modular multiplier can significantly improve the performance. A dedicated FHE hardware accelerator can be used in different devices with varied requirement. Servers prioritize designs for maximum speed. IoT devices prioritize designs for less area and power. For different specifications, there are different design approaches and algorithms to implement modular multiplication. These approaches must be evaluated with the same experimental setup to ensure a fair comparison. It is important to evaluate area, speed, and power accurately. Moreover, modular multipliers are eventually integrated into larger system on chips or SoCs with their own system level constraints, frequencies, and limitations. Therefore, it is essential to explore the design space at system level as well. In conclusion, if we want to explore design space of modular multiplier comprehensively, we need to explore different design approaches, algorithms at block level as well as system level so that it can be used at different devices. This figure shows topology of modular multiplier. Based on design approach, it is classified in two categories, bit serial and bit parallel. Bit serial performs partial multiplication combined with reduction iteratively, while bit parallel performs full multiplication followed by a reduction. Bit serial is further categorized in interleave modular multiplier or ILM and iterative Montgomery multiplier or IMM. Both of these algorithms are commonplace and widely used. Based on its radix, we classify in different variants. For this study, we have focused on radix 2 and radix 4, which are the most basic radix. We could have gone for higher radix, but we can extrapolate its behavior in terms of area, power, and speed from radix from smaller radix, and those requirements lie between bit serial and bit parallel design, and here we are focusing on the extreme part of those designs. Bit parallel designs is categorized in Barrett modular multiplication (BM) and Montgomery modular multiplication (MM). These two algorithms are also commonplace and widely used. In this study, we implement simple Barrett reduction and Barrett reduction with constraint modulus. Same thing for Montgomery as well. Because polynomial multiplication restricts modulus of the form q equal to 1 mod 2n. Hence, using this constraint, we can further optimize bit parallel design. Last row shows the name of the implementation used in this study. Now, let's look how this implementation is designed. This figure shows architecture of Montgomery modular multiplication. Its main components are 3 multipliers, 1 subtractor, and 1 adder. Mult1 performs normal multiplication between operand A and operand B. Mult2 takes product of this operand as input and multiply with minus q inverse. Mult3 takes output of mult2 and multiplies with q. Mult2 and Mult3 along with other hardware such as adder, subtractor, mux and flops performs Montgomery modular reduction. Here Mult1, Mult2 and Mult3 causes critical path delay which reduces the frequency of the whole multiplier. To improve the frequency, we used pipeline multipliers using Wallace tree algorithm. Wallace tree algorithm in synopsis offers 1 to 6 pipeline stages for multipliers. We calculate area and speed for each pipeline stage of multiplier. We select the pipeline configuration with minimum area delay product or ADP. Here figure shows area delay product for different pipeline stages of modulus size 32 Montgomery multiplier. From the figure we can observe that configuration 2.1 has minimum ADP, which means that multiplier 1 has 2 pipeline stages, multiplier 2 has 1 pipeline stage, and multiplier 3 also has 1 pipeline stage. This configuration is required to achieve minimum ADP or maximum efficiency. This figure shows Barrett multiplier architecture. Barrett multiplier also has 3 multipliers, 3 subtractors, shifter, and flip-flops as principal component. We select pipeline stages based on the minimum area delay product of different pipeline as we have seen earlier. Now moving on to bit serial design. This figure shows architecture of interleaved modular multiplier or ILM. Main components are 1 adder, subtractors, multipliers, and flops. Here pre-compute unit calculates multiples of q and operand b. Compute unit performs modular multiplication and reduction with some bits of operand a iteratively. For radix 2, only 1 bit of operand a is used. Compute unit is active all the time, while pre-compute unit is active for few cycles initially. For iterative Montgomery multiplier also, we have similar architecture where we divide it into pre-compute unit and compute unit. This figure shows area and latency of 8 different modular multipliers with different modular size. We use 22 nanometer TSMC technology node. Each design tries to achieve clock period of 250 picosecond. The dashed line over here shows the reference point where the area and latency increases linearly. We have color coded different variants, and for different modular size we have used different shapes. There are 3 main observations from this figure. First, bit serial designs require smaller area but higher latency compared to bit parallel design. Second, Radix 4 designs require large area and lower latency if we compare with Radix 2 designs. Third, bit parallel area triples when modulus size doubles, while bit serial area increases 1.5 times when the modulus size doubles. Here, the modulus size 3264 have so much different design requirement that we cannot compare area and latency. To compare designs of different modular size, we require different parameters. Here we used throughput, area per bit, that is normalized area, and power per bit, that is normalized power, to compare designs of different modular size. To estimate the power accurately, we use PTPX time-based analysis. PTPX time-based analysis requires gate level simulation and realistic test cases to estimate the power. There are three key observations from these two figures. First, bit parallel designs have more than 30 times higher throughput compared to bit serial designs. To achieve this throughput, bit parallel designs require 10 times more area and power to process each bit. Bit serial designs Second, bit serial designs have higher throughput for 32-bit size input. As the input size increases, the throughput decreases. We can see this behavior from bottom left points of two graphs. Third, bit parallel designs are more efficient compared to bit serial designs. For more detailed block level analysis, plots and tables, kindly check out our paper. Now, these variants and designs are integrated in the system level as shown in the figure. Here, multiplier pool has one or more instances of modular multiplier such that the initiation interval of modular multiplier pool is 1 irrespective of which variant it has used. Multiplier controller directly controls the multiplier pool and it controls memory operations using AHP bus. To make sure that the input and output access is continuous to multiplier pool, we need to use dual port memory. AHB bus is also connected with the external host and SOC interface and other memories if needed. Using this system level integration, we have run all the 8 variants of different modular size. We have measured area and power for these designs. This figure shows area for different multipliers. We observe that Radix 2 design require highest area, which is actually opposite to what we have seen in block level analysis. Because to achieve initiation interval of 1 or speed, Radix 2 requires to instantiate more modules which increase its area. When the bit width doubles, bit serial design area quadruples, which is ILM and IIM area. When bit width doubles, bit parallel design increases area 3 times. This figure shows the power of different variants and we can observe that the power estimation closely follows the multiplier area. And here Montgomery multipliers require slightly higher power compared to its area requirement. And here also when the bit width doubles, bit serial power quadruples while bit parallel powers increases 3 times. This table shows comparison between previous work and our work for Barrett multiplication and Montgomery multiplication. For Barrett multiplication, the power saving is 80% and 90% at the same frequency, while the proposed design has only 20% more area. For Montgomery multiplication, the power saving is 61.5% and 49% at the expense of area, where the proposed design has 2 times more area compared to the earlier work. Earlier work and this work has same frequency for Montgomery multiplication as well. Hence, we can say that for Montgomery multiplication, the design has similar characteristic, and for Barrett multiplication, one can say that it has better optimization than the previous design. Hence, our designs are comparable to state-of-the-art work, which makes it suitable for design space exploration as well. In summary, this is the first work that accurately estimates the power for ASIC modular multipliers. We have observed that the bit parallel multipliers are more area and power efficient compared to bit serial designs, even though bit serial design requires less area and power. Barrett multiplier has the highest throughput. We conclude that the Montgomery modular multiplication with constraint modules uses the least area and requires the least power. Hence, it turns out to be the most efficient design if we compare performance, area, and power. We have shared our scripts and designs. To check out our design, kindly follow the link which is shared at the bottom of the page. Thank you.